Bismillahirrahmanirrahim. Assalamu alaikum. Today is the second part of lecture 10. So lecture 10, as we discussed in the last lecture, lecture 10 is divided into two parts, 10A and 10B. So today is the second part. Okay, in last lecture, we discussed about the quadratic residues, and we discussed that for 13 and 13 is partition or non-zero elements of 13 are divided by the quadratic residues and quadratic non-quadratic residues. Okay, so there are equal number of quadratic residues and non-quadratic residues for 13. Okay, so today we will discuss uh, a general result, okay, about the quadratic residue and quadratic non-residue. So we have the result called theorem to every odd prime p has exactly p minus 1 by 2 quadratic residues and p minus 1 by 2 quadratic non-residues. Okay, so move to the proof of this result. Suppose P has K incongruent. Incongruent quadratic residues. And we have to show that K is equal to P minus 1 by 2. Okay, so by lemma 1 that we discussed in the last class, that every solvable quadratic congruence has exactly two incongruent solutions. Okay, we discussed that lemma in the last class. Okay, if this congruence is solvable, then there are exactly two solutions. Okay. Okay, so we apply lemma 1 here. By lemma 1, each quadratic residue yield two incongruent solutions two incongruent solutions. So the total number of solutions is 2k, because there are k incongruent quadratic residues, and every quadratic residue has a solution for a quadratic congruence, and every quadratic solvable quadratic congruence has two incongruent solutions. So there are 12 number of solutions. Okay, sorry, 2 times k number of solutions. But we know that there are p minus 1 non-zero integers or squares of least positive residues. P minus 1 squares of least positive residue. Okay. 1, that is 1, 2 till p minus 1. Okay. So two k must be equal to p minus 1, and this implies k is equal to p minus 1 over 2. So it means p minus 1 by 2 are the quadratic residues. So, and p minus 1 minus p minus 1 by 2 equals p minus 1 by 2 are quadratic non-residues. Okay. Okay, now move to the second result, which is Euler criterion. Okay. We call this as theorem 3. Euler's criterion. Okay. So let P be an odd prime, then a positive integer, a with p does not divide a is a quadratic residue residue of p if and only if a to the power p minus 1 by 2 congruent to 1 modulo p. Okay. In the proof, we will use Fermat's little theorem that we discussed in previous lectures. Okay. Let p be an odd prime, then a positive integer with p does not divide a is a quadratic residue of p if and only if a to the power p minus 1 is congruent to 1 modulo p. Okay? So that's the easiest way to find whether the element is a quadratic residue or not. Okay? So if we know that the element or the integer is a quadratic residue, then we will be able to say that the quadratic congruence is solvable. Okay, so that's a very important result. Okay, now move to the proof. So because we have to show this result with if and only if condition, so we have to show in both ways. So first, we suppose A is a positive quadratic residue. So suppose that A is a say A is a quadratic residue of P. So we suppose that A is a quadratic residue of P, then by lemma 1 or then by definition quadratic congruence x square congruent to A modulo P is solvable, and by lemma 1 it has exactly two incongruent solutions. Okay, so has a solution. Okay, so we assume that let alpha be the solution. Excuse me. So if alpha be the solution and where p and alpha, GCD of p and alpha is 1, so by Fermat's little theorem, or from us theorem alpha to the power p minus 1 is congruent to 1 modulo p. Okay, because p is a prime. So the GCD of alpha and p will be 1. Okay. Okay. Now we have to show a to the power p minus 1. So a to the power p minus 1 by 2 is congruent to, because because a is a quadratic residue and this equation is solvable. So alpha satisfying this quadratic congruence. So we can put alpha here. So alpha squared to the power p minus 1 by 2, which is same as alpha to the power p minus 1, and this is congruent to 1 modulo p. So if we consider the first and the last, so this shows that a to the power p minus 1 is congruent to 1 modulo p. Okay. Now move to the converse part. Okay. Conversely, assume that a to the power p minus 1 by 2 is congruent to 1 modulo p. Now we have to show that a is a quadratic residue, means the quadratic congruence is solvable. Okay, means the quadratic okay. So if a to the power p minus 1 by 2 is congruent to 1 modulo p, then p has a primitive root beta. Then a is congruent to beta to the power k modulo p for some positive integers k. Positive integer k. Okay, where k is less than p minus 1 and greater than or equal to 1. Where k is greater than or equal to 1 and less than or equal to p minus 1. Then taking power p minus 1 by 2 both the sides. So this will be a to the power, or we can write beta to the power k times p minus 1 by 2 is congruent to a to the power p minus 1 a to the power p minus 1 cursor. It's difficult to search cursor because it is very tiny. Okay, a to the power p minus 1 by 2, and this is congruent to 1 modulo p, since beta is a primitive root modulo p. Root modulo p. Okay, so now order of p, order with respect to p of beta is equal to p minus 1, which divides k times p minus 1 by 2. That is k must be an even integer, say k equals 2i, then a equals a congruent to beta to the power 2i is congruent to beta to the power I whole square modulo p. So a is a quadratic because this is solvable. So a is a quadratic. Congruence. Quadratic residue. Quadratic residue of p. Okay, so that completes the proof of Euler's criterion, and this criterion is very useful to find whether the element is a quadratic residue or not. Okay, thank you very much. Allah Hafiz.